But in addition to iron microspheres, there were a lot of what I'll call glassy spheres or droplets. But I noticed that a lot of these glassy droplets were also coming to the magnet. And glass isn't, like in my normal experience, isn't really magnetic.
They don't use a ferrous material
No,
in the production of glass.
You know, not in general. And but what I'm finding is that buried inside of a lot of these droplets are iron microspheres. I think that basically when the heat occurred, there was a lot of massive melting and some mixing that went on. And so a lot of iron microspheres are actually encased in molten glass material as well. So there's a lot of interesting things in there. There are a large number of iron microspheres, which does basically, oh, the other thing that I'd bring up about those, though, is the composition of some of these microspheres does not match the composition of the steel. It was A36 structural steel in the building, and it has a certain manganese content. And I'm finding a lot of microspheres that basically have no manganese in them at all. So what that says to me is that those microspheres aren't actually like structural elements. So my guess is that a lot of the iron microspheres are actually just thermitic residue. Like I said, when thermite burns, it produces molten iron as one of its products. And a lot of these microspheres are, I'm, deducing this, but they match the right composition, because I've ignited thermite chips in my laboratory and basically then gone into them and looked for the iron microspheres that get formed inside of those chips as a part of the combustion. I've made a video of it. And I've looked inside the chips. I've cut them with razors or broken them to look inside the chips before igniting them, and just as a part of my study and analyze of, what is the red material made of. And there's no iron microspheres inside the chips until you actually get them up to the ignition point, which is a little above 400 centigrade. And then they go through this thermitic reaction, and they produce relatively large amounts of liquid iron. I mean, for the volume of the chip, the whole thing basically just melts away inside, and you wind up with actually these tube-type structures where the molten iron melts down through the matrix. It's a silicate-type matrix. And then it basically comes to rest down at the bottom, and it solidifies into a droplet. So they're not perfectly spherical when I do them in the lab, because they encounter an object and they blob out, just like, if I dumped molten lead on the floor here, it wouldn't form into a sphere, it'd form into a puddle. But the point is that the chips produce molten iron, and they're in the dust.
And once again, it's one, why would they be there? And as a person who built aircraft for a living and was paid for doing that and all that stuff, let alone missiles and all that, I knew that we would not use thermitic material to build structures that we're going to fly through the air. Okay. And also, I'm figuring the people in the construction trades, those steel workers, iron workers, and all that, they also, they're not going to be sitting there after welding a building together going, hey, I got this thermitic material. What can I do with it? I can't take it home. I think I'll smear it all over you. Yeah. So the stuff doesn't appear out of nowhere. Who in the past uses that type of material? And
well, there's the thing that you really want to get into here is this isn't traditional thermite. I mean, traditional thermite, pretty much anybody could, make or do things with and so on. This red material is basically, it appears to be a silicate-type structure, which has been made probably through a sol gel process, which the analogy I use for this is kind of like Jell-O. If you mix, the Jell-O pack and water together, when you first mix it together, it's basically like water. But as it sits there and it begins to react, it begins to set up into a solid. And that's basically what the sol gel process does. And then once you've gone into a gel phase, you can either just dry it or you can dry it with compression. You can do various things.
For greater density or something?
Yeah.
Right.
But when they've made the sol gel, what they appear to have done is to have dispersed within that fluid mix before it solidifies nanoparticles of iron oxide and aluminum.
That's very interesting, because just the ability to make nanoparticles. People aren't going to do that in caves, correct? I mean, usually not a good environment for making nanoparticles. They don't do it in bathtubs, to the best of our knowledge?
No, well, you got to be careful.
Okay.
Because you can take certain things, for instance, like iron oxide, and just through regular milling, grinding operations, get them to extremely small, fine dimensions. So, you can. The one.
Still, you'd need some equipment. not
Oh yeah,
happenstance.
well, you know, basically. But the case isn't the same with the aluminum. Okay, you can't just take aluminum and go grind it somewhere and basically get it to form into these very repeatable type structures that we find inside of the chips. I don't know exactly how they make it. I could guess, but I think it's a volatilization process, and then they control the nucleation and so on. But I really don't know exactly.
You're probably right, because as you were saying about grinding and all that.
Well, aluminum doesn't grind too well.
Exactly. Anybody who's ever had a grinding wheel, you don't put aluminum on.
But these don't look like they're ground particles. They're basically, they have a very regular type structure.
Yeah, when you said they were, yeah. That was rather interesting.
We got like 2 minutes left. Can we talk a little bit about like the DSC, information, because you know your
DSC.
average, your average thermate.
Oh, you're liking this DSC?
Yeah, is the red line, and the stuff that you're finding here.
Thank you.
Is active.
Thank you.
So I was wondering if you could like talk a little bit about like its activity in this. Like you could.
I haven't actually done any DSC work. I'm still trying to get access to a DSC. The only thing I've done in the way of you know, looking at the reaction as I go back to, I basically have the ability in my lab to bring the chips up to their ignition point. I can video them, I can study them, you know, before and after to see, you know, the end product from the thermite reaction. I'm still looking to get into a DSC, because what the DSC will do is it quantifies the amount of energy coming out of the reaction. I used to have one in my lab that I worked at back 15, 20 years ago, but I don't have access to one right now, but I am still working on that. And there may be some things happening here in the next few months that are going to give me access to that, but I'm really not sure about it at this point.
Mark, with the minutes that we have, you come here and you come here to learn, and you've learned some stuff already, and hopefully you're learning more, and the viewers are learning more, and I am, and everyone who comes. What was it that like piqued your interest to where most of my viewers maybe think, well, gee, I've got other important things in my life, whatever, soccer game. Why is it important?
Well, in a nutshell, I think we're being lied to, and you know, in essence, it's causing our nation to avoid reality, and you avoid reality at your own peril. I really started questioning it when I first started really hearing about these iron microspheres. That's what really kind of piqued my interest in the first place. I just didn't see that these jet fires were going to have the capability to produce massive quantities of molten steel, and it wasn't within my realm of expectation based on all my engineering experience and you know, working with heat and materials and so on. So you know, that's what got me into it.
Thank you very much for taking the time. I thank you for the viewers. It's good men like you that keep the place good.
Yep.
Appreciate it.